Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be doing a fairly complex RC circuit step response example. And essentially, this is a build-up from the past video, which I will post in the top right-hand side corner of this video right now. So feel free to check that out first before coming to this video. In this example, we're tasked with solving for and graphing v of t and I of t at t is greater than 0. And this v of t and I of t are going through this 0.5 millifarad capacitor. And essentially in the process, we want to solve for v of t and I of t at t is equals to 1 second, 4 seconds, and 5 tau. Again, remember tau is the time constant, right? Which we will be talking about. If you want to try the example and then post your response in the comment section below before watching the rest of the video, feel free to do so. So essentially, what we want to note in this example is that this switch here has been located at point A for a long period of time, and this capacitor here has been charged up. And then at a time period t equals to 0, we flip the switch to this point B, and then we want to analyze what happens at this capacitor. So in this situation, we're going to have two cases where t is less than or equals to 0 and when t is greater than 0. So let's go ahead and take the first case where t is less than or equals to 0. And we want to notice that since this switch has been held at point A for a long time, the voltage across this 0.5 millifarad capacitor will be the same as this 5k ohm resistor, simply because they are both in parallel to one another. So what we're going to say is that v of t at t less than or equals to 0 is equated to the voltage at my 50 ohm resistor, which is equated to just a voltage divider, which is 5k over 5k plus 3k, and this is ohms over ohms, so they cancel out, times this 24 volts at my source here. And essentially what I end up getting is 15 volts when I do the math. And from our previous studies, again, I explained this in what is a capacitor video. We noticed that voltage cannot change instantaneously in a capacitor. So the voltage at 0 minus must equate to the voltage at 0 plus, or right when the switch goes to position B, which we just say is the voltage at 0. And this has to equals to 15 volts. And this is what I call my initial condition. And that is it for case number 1. So then for case number 2, we want to understand what has happened to capacitor at t is greater than 0, or when this switch goes to position B. And we know that from our past video, we say that v of t is equated to v of infinity, or the final condition, plus this v of o, the initial condition, which we already found, minus the final condition again, times this exponential e to the minus t over tau. So we should note that we have this value already, which is 15. So we need to find this final value, and we need to find tau. So then we can say then that tau is equals to R Thevenin times my capacitor. And this R Thevenin, as we've discussed in another video, is the total resistance of my capacitor sees. So if I look into here, A, B, the resistance that I see is this R Thevenin. And this R Thevenin is essentially just going to be 4K, and my C is 0.5 millifarads. And essentially when you do the multiplication, this becomes 4 times 10 to the third times 0.5 times 10 to the minus 3. So then this just becomes 4 times 0.5, or 4 divided by 2, which is just 2 seconds, which is equals to tau. So then the next thing we need to find is what my V final value is going to be. And we notice that this is the only source in my circuit. So as time goes on, my final voltage will saturate to just 30 volts. And now we can go ahead and plug everything into our equation and say then that V of t is equated to this 30 volts plus 15 minus 30 e to the minus t over 2, which then, if you notice, this becomes 30 minus 15 e to the minus 0.5 t. And this is in volts. So therefore, we've solved for V of t at t is less than or equals to 0, and we've solved for V of t at t greater than 0. So let's be explicit here. So V of t is equated to this 15 at t less than or equals to 0, and 30 minus 15 e to the minus 0.5 t at t greater than 0. And again, this is in volts. So then the question then follows up and asks us to solve for t at 1, 4, and 5 tau. So essentially, at t is equals to 1, V of 1 is 30 minus 15 e to the minus 0.5, which is going to be this 20.9 volts. At t is equals to 4, we get V of 4, which is 30 minus 15 e to the minus 2, which is 27.97. And at t is equals to 5 tau, we know tau is equals to 2. So then this is V at 10, which is 30 minus 15 e to the minus 5, which is equals to 29.8. As you can see, this is getting closer and closer to that 30 volts. So then the final thing we have to do for this part of the problem is graph V of t so that the viewer can visualize this circuit and what it's doing. So in my y-axis, I have V of t, and in my x-axis, I just have t. And let me go ahead and put some markers here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I know that at 0, this is going to be 15. At a point 1, it's going to jump up to 20.9. At a point 4, it's going to jump up to 27.97. At a point 10, it's going to jump up to 29.8. And essentially, it's going to saturate at 30. Again, this is in volts. So let's go ahead and say then that at my time less than or equals to 0, it's going to go all the way to 15. And then at 1, it's going to be at 20. At 4, 27.97. And at 10, 29.8. All right, and this is my saturation line here. So essentially, it's going to go something like this. Right? And the reason why I wanted to plot this 5 tau is because engineers consider 5 tau to be the end of the transient state or the beginning of the steady state. So what I mean by that is from here to here, this is the transient state. Or essentially when the voltage across my capacitor has not reached its full potential of 30 volts or its final value. And essentially here, after 10, we call this steady state. So I hope this makes sense for my voltage. Let's go ahead now and do the current. So then to get current, I of t, we know that the current through a capacitor is going to equate to the value of that capacitor times the change in voltage over the change in time. So then this just becomes 0.5 millifarads times the derivative d over dt of my 15 volts for t less than or equals to 0, and d over dt of 30 minus 15 e to the minus 0.5 t for t greater than 0, and this is in volts. So then we can continue and say then that I of t is equated to d over dt of 15, our constant, is simply just 0 for t less than or equals to 0. And then for my second case here, I can say that this becomes 0.5 millifarads times the derivative of 30 is 0 minus the derivative of this chunk becomes 15 times negative 0.5 e to the minus 0.5 t. And again, this is all in amps now, and this is for t greater than 0. I'm going to rewrite this as 0.0037 e to the minus 0.5 t. Again, amps. And then ultimately this just becomes 3.75 e to the minus 0.5 t milliamps for t greater than 0. So then knowing this, we can say that at t is equals to 1, I of 1 is equated to 3.75 times e to the minus 0.5 milliamps, or just 2.27 milliamps. And then at t is equals to 4, I of 4, if you plug it into this t here, you're going to get 0.507 milliamps. And then at t is equals to 5 tau, you're going to get I of 10, which is equated to 0.0252 milliamps. And as you can see, the current is slowly going towards 0 amps. And this is essentially because as the capacitor charges, it reaches steady states and becomes an open circuit. So 0 current passes through. So let's go ahead and finalize this example by graphing for I, similar to how we did voltage. This is I of t, and this is in amps, or let me say milliamps. And this is in t, which is in seconds. Let's say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then the points that we care about are going to be 3.75. Again, this is in milliamps. We care about 2.27, and then we care about 0.507, and then we care about this 0.0252. All right, and then it saturates, let me call this 0. So then what actually happens is that there'll be 0 current flowing all the way into time 2, and then it's going to shoot up. It's going to be a rush of current. All right. And then it's going to be at 3.75 again, because if I plug in 0 here for t, I get 1, and then 1 times 3.75 is just 3.75. At t is equals to 1 second, it's going to be at 2.27. At 4 seconds, 0.5, and at 10 seconds, 0.02. So essentially, it's going to decay exponentially like this, and this is going to be my graph. So to finalize this, this here is what we consider our transient state. So current is flowing. And this here is what we consider our steady state, essentially where no current is flowing. Okay, if you like the video, please give it a thumbs up and share the video. If you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.